Welcome to our deep dive on Chapter 6, Electromagnetic Induction, from your Class 12 Physics textbook.
Oh, this is a good one.
It is a good one, and huge thanks to India's National Council of Educational Research and Training,
NCERT.
for making this chapter freely available.
For everyone.
Yeah, for everyone, and we're here to break down this awesome chapter, especially for you, our 15-year-old student listener.
You know, it's fascinating how electricity and magnetism used to be considered completely separate things.
Right, like two totally different worlds.
Yeah, totally different world.
But then, boom, scientists like Oersted and Ampere made this incredible discovery.
Yeah.
Moving electric charges create magnetic fields.
It really revolutionized the way we thought about these forces.
Exactly. And so if moving electric charges can create magnetism,
Right.
could the reverse be true? Could magnets somehow create electric currents?
It's the next logical question, right?
It seems like the next logical question, yeah.
Yeah.
So that's where the brilliant minds of Michael Faraday and Joseph Henry come in.
Around 1830, they independently conducted groundbreaking experiments that revealed a deep connection between magnetism and electricity.
So tell me about these experiments.
Right.
What did they do? What did they find?
Okay, so picture this Faraday has a coil of wire connected to something called a galvanometer,
Okay.
which is basically a fancy instrument for detecting electric current.
Okay.
Now he takes a bar magnet and moves it towards the coil.
Okay, I'm visualizing it. So he's moving the magnet, then what?
Well, as the magnet moves, something amazing happens. The galvanometer needle deflects,
Okay.
showing that a current is flowing through the coil. But here's the catch.
Okay.
The current only flows when the magnet is moving.
Oh, so it's the motion of the magnet that's creating the current. That's pretty wild.
It is, and Faraday went even further and replaced the bar magnet with another coil carrying an electric current.
Okay.
And guess what happened when he moved the second coil relative to the first one?
Let me guess, a current was induced in the first coil.
You got again, the relative motion between the coils was the key.
Wow.
It didn't matter if it was a moving magnet or a moving coil carrying current. As long as there was a relative motion, an electric current was induced in the nearby coil.
Okay, so we've got moving magnets and moving coils creating these invisible forces that can induce electric currents, but there's more, right?
Yes, much more. Faraday wasn't done yet. He conducted a third experiment.
Okay.
That really shook things up. This time, he kept the two coils stationary, but changed the current flowing through one of the coils.
So no more physical movement, just changing the current. What happened?
Even without any physical movement.
Wow.
Simply changing the current in one coil caused a current to be induced in the other coil.
It's like some invisible force is bridging the gap between them.
Exactly. And this, something that Faraday brilliantly identified, is what we now call magnetic flux.
Okay, so let's unpack this idea of magnetic flux.
Okay.
It sounds pretty important. What exactly is it?
Think of it like this. Imagine you have a sprinkler, spraying water droplets. The number of water droplets passing through a particular area, like a window, would represent the flux of water through that window.
So it's like a measure of how much of something is passing through a given area.
Yeah.
But how does this apply to magnetism?
Well, in the case of magnetism, we're not talking about water droplets, but about magnetic field lines. Magnetic flux, represented by the symbol AB, is a measure of the number of magnetic field lines passing through a specific area.
Okay, so it's like counting the imaginary lines of magnetic force
Yes.
passing through a surface.
Yes.
But the strength of a magnet doesn't change, right? So how can this flux change?
That's right. It's not just about the strength of the magnet itself,
Okay.
but also about how it's positioned relative to the surface. If you change the angle between the magnet and the surface, you change the number of field lines passing through it.
I see. So it's kind of like tilting the sprinkler.
Yeah,
You can change the amount of water hitting the window, even if the water pressure stays the same.
that's right.
So this magnetic flux, is that what's inducing the electric current?
Yes. Faraday's brilliant insight was realizing that it's the change in magnetic flux,
Okay.
not just the presence of a magnetic field that induces an electric current. And he even came up with a law to describe it.
I bet this is Faraday's famous law of induction, right?
You're absolutely right.
I knew it. This is where things get really interesting, I'm sure.
Faraday's law of induction basically states that the magnitude of the induced electromotive force, which is essentially a fancy word for voltage, is directly proportional to the rate of change of magnetic flux.
Okay, that sounds pretty important, but can we break it down a bit? What does it actually mean in simpler terms?
Sure. Essentially, the faster the magnetic flux changes, the greater the induced voltage. Think of it like this. If you move the magnet quickly towards the coil,
Yeah.
You're changing the magnetic flux more rapidly, and that creates a larger induced voltage.
So it's like pushing the magnet really fast through that imaginary window.
Yeah.
More field lines pass through in a shorter time, which creates a stronger electrical push.
That's a great way to visualize it. And this induced voltage is what drives the current through the coil.
Okay.
The greater the voltage, the greater the current. It's all connected.
This is pretty amazing stuff. We've gone from basic magnets and coils to this concept of magnetic flux.
Right.
And how it creates electricity. I'm starting to see how this all fits together, but there's more, right?
Oh, definitely more. In fact, there's another important law that comes into play here.
Okay.
Lenz's law.
Okay, I'm intrigued. What's Lenz's law all about? What does it tell us?
Lenz's law is all about the direction of the induced current.
Okay.
It states that the direction of the induced current is always such that it opposes the change in magnetic flux that produced it.
Wait, so the induced current actually fights back against the change that created it?
Yeah.
That's kind of strange, isn't it? Why would it do that?
It might seem counterintuitive, but it's a fundamental principle related to the conservation of energy. Nature doesn't like getting something for nothing. Think of it like this. If you try to push a heavy object, it resists your push.
Right.
It doesn't just start moving effortlessly.
Okay, I see the analogy. So the induced current is like the heavy object.
Yes.
Pushing back against the change in magnetic flux.
Exactly.
But how does this actually play out in the experiments?
Okay, well, let's go back to Faraday's first experiment.
Okay.
Remember, he moved a magnet towards a coil, inducing a current. Lenz's law tells us that the direction of this induced current will be such that it creates its own magnetic field that opposes the approaching magnet.
So the coil basically becomes a little electromagnet trying to push the approaching magnet away.
Exactly. It's like a magnetic tug of war. And if you were to pull the magnet away from the coil, the induced current would reverse direction, creating a magnetic field that tries to attract the magnet back.
So the induced current is always trying to maintain a kind of balance.
Yes.
Opposing any change in magnetic flux.
Yes.
It's like nature's way of keeping things in check.
Precisely. And this principle applies to all sorts of situations involving electromagnetic induction. It's a key concept for understanding how generators, motors, and many other devices work.
Wow. I'm really starting to appreciate the elegance and complexity of this whole phenomenon.
Yeah.
We've gone from simple experiments to fundamental laws of physics, and it's all connected. And this is truly a deep dive.
It is. It really is. And speaking of connections, you know how we talked about moving magnets inducing currents? Well, what happens if the conductor itself is moving through a magnetic field?
Oh, that's a great question. I'm ready to dive even deeper into this. What happens then?
That's where the concept of motional electromotive force, or motional EMF, comes in. Imagine you have a straight conductor, like a metal rod, moving through a magnetic field.
Okay, I'm picturing a metal rod moving through those invisible lines of magnetic force.
Yes.
What happens to the rod?
As the rod moves, it actually generates an EMF, or voltage, across its ends.
So simply by moving a conductor through a magnetic field, we can create a voltage. That's incredible. What factors affect the strength of this induced EMF?
Well, the strength of the magnetic field definitely plays a role. The stronger the magnetic field, the greater the induced EMF, and the speed of the conductor also matters. The faster the conductor moves, the larger the induced EMF.
So it's all about motion and the strength of the magnetic field.
Yes.
Is there a way to calculate this motional EMF?
Absolutely. There's a handy formula for that Iroquois BLV, where A represents the induced EMF, B is the magnetic field strength, AL is the length of the conductor, and V is its velocity perpendicular to the magnetic field.
That makes sense. So the longer the conductor and the faster it moves through a stronger magnetic field, the greater the induced EMF. It's all proportional. That's pretty amazing. It's like we're unlocking the secrets of how to generate electricity from simple movements and magnets.
It is quite remarkable, and this concept of motional EMF has many practical applications. It's the basis for how generators work, converting mechanical energy into electrical energy.
Speaking of generators, I know they play a huge role in our modern world. We rely on them for electricity every day. But before we jump into that, there's one more concept. I'm curious about inductance.
Okay.
What exactly is inductance?
Inductance is a fascinating property of electrical circuits, especially those containing coils. You can think of it as a coil's resistance to changes in current commutativity. It's kind of like inertia in mechanics, where an object resists changes in its motion.
So a coil with high inductance doesn't want the current flowing through it to change too quickly.
Right.
It wants to maintain a kind of electrical stability.
Exactly. Inductance, represented by the letter L, measures how strongly a coil opposes changes in the current flowing through it, And there are two types of inductance, self-inductance and mutual inductance.
Okay, two types of inductance. Let's break those down. What's self-inductance?
Self-inductance describes how a coil induces an EMF in itself when the current flowing through it changes.
Wait, a coil can induce a voltage in itself? How's that possible?
It might sound strange, but remember Faraday's law, any change in magnetic flux through a coil induces an EMF. Well, when the current through a coil changes, it creates a changing magnetic field around the coil, which in turn changes the magnetic flux through the coil itself.
So it's like a self-perpetuating cycle. A changing current creates a changing magnetic field, which then induces an EMF in the same coil that created it.
Precisely. And this self-induced EMF always opposes the change in current that produced it. It's like the coil is trying to maintain its current state, resisting any sudden changes.
Like the coil has a mind of its own trying to keep things stable.
Yeah.
This is pretty mind-bending. But you mentioned another type of inductance, mutual inductance. What's that all about?
Mutual inductance describes how a changing current in one coil can induce an EMF in another nearby coil.
So it's like a magnetic conversation between coils.
Yeah.
One coil changing its current can influence the other.
That's a great analogy. Imagine two coils placed close to each other. If you change the current flowing through one coil, it creates a changing magnetic field that extends to the nearby coil, inducing an EMF in that second coil.
I'm starting to see how this concept of inductance, both self-inductance and mutual inductance, plays a crucial role in many electrical circuits and devices.
Absolutely. Inductors, which are essentially coils designed to have specific inductance values, are used in all sorts of electronic circuits. They're essential components in transformers, filters, oscillators, and many other applications.
It's amazing how these fundamental principles of electromagnetism have led to so many practical inventions that power our modern world. It makes you wonder what other secrets are hidden within these invisible forces.
It really does. And speaking of hidden secrets, did you know that inductors can also store energy, just like capacitors store electrical energy in electric fields? Inductors store energy in magnetic fields?
Okay, now I'm really intrigued.
Yeah.
I know capacitors store energy like tiny electrical reservoirs, but how do inductors store energy in magnetic fields?
When current flows through an inductor, it creates a magnetic field around the coil. The energy needed to establish this magnetic field is stored within the inductor itself. It's kind of like stretching a rubber band. You're storing potential energy in the stretched rubber band.
So the energy stored in an inductor is like the potential energy stored in that stretched rubber band. And when the current stops flowing, the magnetic field collapses, releasing that stored energy.
Exactly. It's a fascinating process, and the amount of energy an inductor can store depends on its inductance and the amount of current flowing through it. The formula for the energy stored in an inductor is UB equals 1/2 Li squared, where UB represents the stored energy. L is the inductance, and I is the current.
This is incredible. We've gone from moving magnets to invisible fields to coils that can store energy. It's like we're unraveling the mysteries of the universe one step at a time.
It truly is an amazing journey of discovery. And speaking of amazing discoveries, are you ready to explore one of the most practical and impactful applications of electromagnetic induction?
I'm definitely ready. What are we diving into now?
It's time to explore the world of AC generators, the machines that power our homes, industries, and essentially our modern way of life.
Okay, let's shed some light on how these amazing machines work. I'm ready to be enlightened.
Okay.
Bring on the AC generators. I'm eager to understand how these workhorses of the modern world harness electromagnetic induction.
Well, imagine a coil of wire called the armature spinning rapidly within a strong magnetic field.
Okay, I can picture that, a spinning coil surrounded by those invisible magnetic forces. What happens next?
As the coil spins, it continuously changes its orientation relative to the magnetic field, right?
Right, so the number of magnetic field lines passing through the coil, the magnetic flux, is constantly changing as the coil rotates.
Exactly. And according to Faraday's law, that changing magnetic flux induces an electromotive force, or EMF, in the coil.
So the spinning motion of the coil within the magnetic field is generating a voltage. That's how we get electricity.
You got it. But there's a clever twist to how this induced EMF is harnessed to produce alternating current, or AC.
Okay, I'm all ears. How do we get from this spinning coil to the AC power that flows into our homes?
Picture this. The ends of the spinning coil are connected to two separate rings called slip rings,
Okay.
which rotate along with the coil's stationary brushes make contact with these slip rings, allowing the induced current to flow out to an external circuit.
So as the coil spins, the brushes are constantly collecting the induced current from the slip rings, But why is it called alternating current? What makes it alternate?
That's where the magic of the design lies, as the coil rotates, the direction of the induced current changes every half turn.
So for half a rotation, the current flows in one direction,
Uh-huh.
and then for the next half rotation, it flows in the opposite direction. That's how we get the alternating back and forth flow of AC power.
Precisely, the induced EMF in the coil, and therefore the current it produces, alternates in direction. As the coil spins, this alternating current flows through the brushes, out of the generator, and into the power grid, eventually reaching our homes and powering all sorts of devices.
Wow, that's brilliant. Just a spinning coil and some clever engineering. And we can harness the power of electromagnetic induction to generate the electricity that powers our world. It's mind-blowing to think that this all stems from the fundamental principles we've been discussing.
It really is a testament to the ingenuity of those who figured out how to put these principles to work, and the scale of these AC generators is impressive. Commercial power plants use gigantic generators that can produce hundreds of megawatts of power.
That's enough to power entire cities. It's amazing to think that it all comes back to the simple yet profound discoveries of Faraday and Henry. Their work truly laid the foundation for our electrified world. But I'm curious, what makes these giant generators spin in the first place? Where does that mechanical energy come from?
That's a great question. The source of the mechanical energy can vary depending on the type of power plant. Some generators use the force of falling water from dams to spin turbines connected to the armature. Others use steam produced by burning fossil fuels or from nuclear reactions.
So whether it's the relentless force of a waterfall or the heat generated by a nuclear reaction, we're ultimately using nature's power to turn those coils and generate electricity.
Exactly. And it's a beautiful example of how scientific principles, once understood, can be harnessed to solve real-world problems and create technologies that improve our lives.
Well, I have to say, this deep dive into electromagnetic induction has been truly enlightening. We've covered a lot of ground, from the basic experiments of Faraday and Henry to the intricacies of Lenz's law and the practical applications of generators. It's amazing to see how it all fits together like pieces of a giant puzzle, revealing a bigger picture.
It's been a pleasure exploring this fascinating chapter of physics with you. And for you, our student listener, I hope this deep dive has sparked your curiosity about the world around you.
Absolutely. As you continue your studies, keep looking for examples of electromagnetic induction in action. You'll find it everywhere, from the motors that power your electric toothbrush to the wireless chargers that power your smartphone.
And always remember to ask questions and explore deeper. Who knows, maybe you'll be the one to make the next groundbreaking discovery in this field.
So keep that spark of curiosity alive. Keep exploring, keep learning, and keep pushing the boundaries of knowledge. The future of science and technology is in your hands. Thanks for joining us on this electrifying journey.